Good morning, everyone. Welcome to the second day of the second Wyoming Computing Symposium. The focus of this year's symposium is on data analytics, computing advances for drone applications. So yesterday, we got to listen to many cool applications, as the people shared with me, that it was really nice to see all the places like people were using drones for, and the advances they have made in processing terabytes worth of data. That was the main focus of this event. And now we have few people who are going to share their experiences. But before that, not everybody was here yesterday, so I want to start with thanking the people who worked behind the scenes. So it's always easy for people like me to come and talk it to everyone, show our face. So we'll start with Judy Yates, who did a lot of work, and thank you, Judy, for helping. And you all got those very nice flyers, announcements, everything. Donna here, she was the one who prepared. And in the GIST program, Tom, he's here because he had, who knew, I think family reunion, so he had to go for that one. He also put together a lot of bits and pieces to make this event happen. And Beth Leonard, who is, I think, making all the budget allocations and things like that. She's not here. Maybe she is processing all our travel reimbursement requests, so on and so forth. Let's give her a thank you for Beth Leonard. And similar, yesterday, everything went so well. I have to thank two people. One is Valerie for running all the slides. Sorry. See, I need to have my coffee. I'm sorry. Natalie, who ran all the slides without any glitch. But the second person is, again, in the back from the IT department. So I don't know whether everybody got a chance. The video from yesterday is all posted in YouTube. So thank you, sir. It was really great, and we look forward to having these talks recorded and posted there. So without further delay, it's my pleasure to invite Professor Melissa Reynolds, a professor in the Department of Chemistry at Colorado State University, who will be giving the opening remarks for today's events.
Good morning, everyone. It is such a pleasure to be here today. As I mentioned, or as was mentioned, I am Melissa Reynolds. I'm a professor in chemistry and biomedical engineering. But the other hat that I wear is in the Office of the Vice President for Research, working with Dr. Mosley and other members of our team there, focusing on research infrastructure. So broadly defined core facilities, which would be things that like the physical nature of things like NMRs for chemists, or mechanical device testing for engineers, or survey design and development for folks in College of Liberal Arts. And so it's very broad. But the most latest that we have worked really closely with Michael Kirby and others to think about on campus is what should CSU be doing in the areas of high performance computing. And so this partnership and this opportunity that I had yesterday to learn about what is going on up here, which is fabulous. Actually, I should have said that loudly, which is fabulous, and really deserves, as was pointed out multiple times yesterday, really the highlighting of what is going on. And so we really look forward to partnerships with you and others and thinking about how can we do this better, not only within HPC and drones, but also in biosecurity, also in thinking about how do we actually secure data in a way as we're doing processing that makes it more available to our researchers, right, in a form that also meets their needs. And what is exciting to me about this particular field, in addition to all of the data and collection that we can do, is also then how fast it changes. So, right, in many other fields, we move at a speed, let's just call it slower. And in this field, what excites me even more is we have to move fast, right? If we aren't moving fast, then we're behind. And so you all have a really great opportunity to really set the pace for innovation and entrepreneurship and discovery, and all of the other fields really are going to be looking to you and what we can do together as we continue to move forward. So I am excited today to learn even more about what is going on, not only here at Wyoming, but also around the country and eventually around the world as too. So again, I appreciate the discussion that we had yesterday. This is one of the first conferences that I have been to kind of in the last couple years where the discussion was really vivid, right? You ask questions of the audience. You guys actually said something. This is fabulous. And so this also tells me really what a great community we have here, right? The ability to have that dialogue, the ability to challenge what somebody's saying, the ability to say, hey, have you ever thought about this? Right? And then the discussion can go on and on and on, right? Without those, what I like to call the academic pauses. Right? In our classrooms, we count to 10 and hoping one student will say something, right? But we don't have to count to 10 here, right? There's always people wanting to say more and talk even afterwards and in the poster sessions and at lunch. And you know, one of the things the governor said yesterday that was really inspiring was, you know, we really look to solve problems and we want to solve them together, not based on particularly a set of regulations, but how are we solving that problem that's actually going to move us forward in a timely manner? And to that, we need creative minds that are focused on problem solving. Well, luckily, universities have that. We are trained and we are hired to solve problems in the most creative ways that we possibly can. So with that, I know our keynote today, because that is not me, has solved lots of problems in this field, and of this has really set us forward in ways of thinking about problems in new ways and advancing the field. So with that, I will turn over to the next speaker to do next introductions, and thank you again for inviting me and including CSU and all the organizers and everything you've done. This has been the most probably fabulous 2 days of my fall semester so far. So thank you very much.
So thank you, Dr. Reynolds, for inspiring us, you know, to look into solving problems in a collaborative way, reminding that piece from the talk yesterday. It's great. Now, I don't know, Donna, I think if we know each other for 8+ years, I think I can tell whatever I want about you, I guess. Okay. All right. So it's my absolute pleasure to introduce today's keynote speaker. So we are all part of the America View family, you know. So she runs the Idaho View program. A long time ago, they used to rotate because they have 3 universities in Idaho. So somebody mentioned, oh, we are going to have a new person take over the Idaho View program. And they say, oh, who is that? And it turns out it was Donna. And most of the people, when they join the America View, they will always say, like, oh, I'm new. I'm wanting to know what you guys are doing. I want to. But from get-go, Donna was ready. We learned that not only most of us do satellite remote sensing, but she also had a very strong research program in the drone, not just using data, and we learned quickly how many different things she has done, whether it's agriculture, forestry. She will tell all about that. It's an absolute pleasure to have. It's a great leader. She is now serving on the America View Board of Directors. This is your first time you are in the board, and it's a great colleague to work with. So if anybody has interest, you know, Dr. Allen mentioned we need to start thinking about writing joint proposals with Idaho State University. I can put words in your mouth. She will be very happy to discuss with you to start those joint proposal opportunities. So without further delay, you know.
Thank you, Ramesh, and thank you everyone for attending my talk today. I'm going to kind of talk about the sky is the limit with drones and drone data and all the things that we can do with it. And for today's talk, I'll kind of introduce a little bit about myself, some of the challenges we face with data processing and how we can leverage high-performance computing to kind of handle some of those high-performance needs of big data that we get with our drone sensors, and then provide some real-world examples of how we're using drone data to solve problems, those problems, complex problems that we face, especially in the environmental field. Just a little bit about myself. I've been flying drones now for about 13 years, and I really got interested in flying drones because at the time I was actually doing work in Hawaii, and there was problems getting like good high-resolution imagery for land management, environmental types of problems. So that sort of started a foray in, we need to have better data to answer these challenging questions. So over that time, I've been through all kinds of crazy FAA rule changes, which some of you are probably familiar with, kind of even starting from the time where I had to hire a pilot, a licensed pilot, to actually be on site while I flew a drone, because at the time you had to have a pilot's license to fly in the national airspace, going through an extensive COA process to fill out paperwork to even be able to fly, and then seeing those regulations and rules change over time, and until we encounter new problems like today about flying drones that are blue list. If you haven't heard about blue list drones, or NDAA compliant, so drones that are not typically manufactured in countries that are prohibited. So kind of through all that experience, I've been tackling a lot of different challenges, moved from Hawaii to Idaho, always loved Idaho, and wanted to kind of take a big step into looking at problems to solve in our part of the world. So that is involved using a lot of different sensors. This is a combination hyperspectral sensor, LiDAR sensor. And when we're thinking about these sensors, one flight for this particular sensor setup produces 50 gigs of data. So thinking about has huge data challenges, not only for processing, but for data storage and for analysis. What we've been doing kind of in Idaho is working together amongst universities. This is a project where we're bringing together universities from all over Idaho, working together to bring biologists and professional people from the field, looking at bringing students from high schools together to learn about how to use this technology. And just like Wyoming, we are an X4 state. So X4 states oftentimes band together for joint research projects, and we have a lot of similar types of questions about environmental concerns. So as Ramesh mentioned, please do approach me, and I would be really excited about these opportunities we have to collaborate amongst our states and find those kind of collaborative opportunities that meet kind of our similar objectives. Also for our programs, we really are trying to get students with hands-on experience collecting data, getting their pilot's license, making sure that they're able to process and collect data. It's one thing to fly a drone, but it's another thing to take that data and process it and come up with a solution for analysis. In this particular example here, students were looking at flying. I do love this particular drone because I can throw a lot of different sensors on it. Here I have RGB in the front, thermal on the back, and for this one actually I often throw oblique cameras on the sides so that we can get side views as well. stitching all that together, data together, fusing it, and then looking for, in this case, and I think there was another talk about salmon reds or salmon nesting, trying to find thermal refugia. So as we're seeing salmon populations declining, how can we look at river systems and map them? Where are the red nests located? Where are we seeing different temperature regimes, and how we can maybe look at some predicting and forecasting. And then, of course, providing students with opportunities to try all different kinds of platforms, and working with our partners to kind of test these little platforms out and see what is most appropriate for what type of problem that we're trying to solve. We've been flying a variety of different platforms. More recently, I mentioned NDA compliant or blue list drones. Those types of drones that we're flying now, we've been kind of going through generations of different types of drones. Our kind of newer ones that we're using are the Quantum Systems Trinity Pro. This is a really nice platform. I've got a LiDAR sensor, multispectral sensors that match up with our Sentinel or satellite imagery bands. And then another NDAA or blue list drone. Here's an inspired flight drone, so that we can use these drones to capture data. And usually what happens is we end up with gobs and gobs of data, and then sometimes there's that data bottleneck to processing. So what we want to do is take our LiDAR data, take our image data, stitch it together, and produce products that we can do some analysis with. And this is where we've started to take a step into the high performance computing. And this, of course, is where Wyoming excels, University of Wyoming Computing Center, in having high performance computing to crunch this data and process it. And we have a little system that we've been using at Idaho State University, a GPU type of unit, where we take multiple graphics cards, stack them together, and then use it for the very graphical image matching, image sort of stitching together, and then processing of the data, and then now doing analysis. So this has been a really step up in helping solve that bottleneck problem of processing these big data sets. I'd like to kind of now step into a few examples of some projects that we're working on that leverage some of this high performance computing and take a step into some of the machine learning and AI. Let's go. So this is one of our projects. This is along the Snake River. And along the Snake River, we have a huge golden eagle nest population. This is one of the largest raptor nesting areas in the country. And there's been a decline in nest productivity. So you can see here a couple of nests is a little bit dark, but here and there. And this is from imagery captured by a UAS. So of course, I'm working with partners at Boise State University from the Raptor Center. And so we have biologists on site, and we've been making sure that we have full permission. This is actually on BLM land where we have permission to fly, and we're keeping a safe enough distance away from the birds, and then having biologists spotting scopes on site to make sure that there's no disturbance. We're looking at creating as part of step one, an inventory of all these nests along this 50-mile corridor of the Snake River. So these our birds are cliff nesting species, and they're choosing different sites every year. And some of these sites some challenges. For example, there is a parasite that now it's not getting cold enough to kill that parasite over winter. It's a chicken bug. And that chicken bug, when there's little nestlings in the nest, basically is a parasite that sucks the blood of the chicks. And the chicks become so stressed that they're actually jumping out of the nest before they're fully fledged. So they're very depleted and facing challenges from just different climate change issues that are impacting their survivability. So we've been looking at what nests are successful, what nests are thriving, what nests are not, and being able to work with our biologist partners to look at how can we model this and look for things like nest sites that have a different solar radiation. So going to our GIS remote sensing, now we can start bringing in different modeling factors. Solar radiation, looking at cliff location aspect, and starting to model where are nests more or less successful. So these birds are difficult to monitor. They're in remote locations and often inaccessible. Some of these nest sites are really only accessible by boat to view what is going on in the nest. The other thing I'd like to point out is this is a Google Earth image. And of course, when we're looking at imagery from Google Earth, a lot of times vertical cliff face is just a black blob, often shadowed. If you look at it, it's often stretched. We don't get that nice detail that you saw from our drone imagery. So when we're looking at monitoring these birds in the field, we're looking for opportunities to make efficiencies using AI or recognition of these different nest sites. And then again here, we have not only kind of issues with top image here, Google Earth. Here's our kind of drape of our cliff imagery with our nests, is that these nest locations are in 3D. So often, how do you map? If the biologist is out in the field, especially those two nest sites that were close together, how do you know which one they were using? How do we map that location? And so that was another issue we were trying to address with biologists. How can we actually pinpoint and map those locations in this 3D environment? So we created a large data set, image acquisition over a couple of years, and did some pre-processing and started to create some training and validation sets for machine learning. And for our first iteration, we were using kind of a YOLO, you only look once, training model approach, and then looking at kind of identifying birds automatically in our imagery, and then looking at future predictions. So when we are kind of building our models, we were looking at doing some annotation, so annotating our images, and we are annotating it in our YOLO modeling environment here. We could actually model what an empty nest was, do some close-ups here. So here are a couple of empty nests that we've annotated. And here you can kind of see the end result. We're looking at taking that YOLO model and then looking at kind of the mean average precision. What kind of value is the computer predicting as to the likelihood that this is identifying a nest correctly? Here we have a nest with an adult in it. And so being able to train these models has been really helpful when we look at our data set of 50 miles of cliff imagery. Now we don't have to manually go through all those images. We can run it through our YOLO model and have this automatically be identified by using these machine learning approaches. One thing we noticed, and probably similar to here, is that there's been issues with invasive species, invasive plant species. So tumbleweed, tumble mustard, and kind of a surprise to us and surprise to our land management partners was over these cliffs, all these tumbleweeds are blowing over the cliff edge and dropping into nests. And they totally are filling up nest sites such that they're no longer even able to be occupied by a eagle. So that was interesting to be able to also identify, hey, we've had a whole bunch of nest sites now that have been taken out of the options for birds to select. And again, here is another threat, these threats, this weedy debris piling up in these nest sites. We've also been kind of looking at, this is, stage one was looking at imagery. Now we're looking at using LiDAR data. And with LiDAR data, what this is really helping us with is pinpointing exact location with an XYZ coordinate that we can go back to and reference again and again. So in this kind of approach, we've kind of started off with kind of using YOLO models, and now we want to kind of take it to potential future real-world identifications in the field as we're out flying, being able to have that real-world deployment, and starting to leverage some of our high-performance computing devices. So we've been actually looking at some tools that we can take out into the field with us to run some of these models in real time, and then bring it back, plug it in, and then have that as part of our cloud processing model. So just a little bit on our initial results for modeling those locations using training and test data. And then kind of leading into, well, how is that impacting the nest sites? So something that was a new discovery was, hey, this weedy material is piling up everywhere and interfering with nest sites. Here you can see this is actually Crater Rings near Boise area. We're looking at different nest sites. These little dots are nest sites. And this is where we're bringing in remote sensing and GIS modeling, looking at thermal radiation, and looking at aspect, direction. And those years represent kind of when they were last occupied by a particular nesting pair of eagles. In this particular model, again, just a simple GIS model looking at different characteristics here that help identify where is appropriate or suitable modeling or suitable nest sites for our birds. And what we end up with is this really thin little red area. So here we think, oh wow, there's all this great habitat out there for birds to nest. But when we look at where they can actually nest, it turns out to be a very, very small area. And what we found here in the 1988 and 1976 sites, the reason that they haven't been occupied is, as my student discovered as she was walking up there and neck deep in tumbleweed and tumble mustard, was that they were completely buried underneath this weedy debris. So being able to kind of make these kind of unexpected discoveries as we're kind of using the data has been really helpful. And then for our biologists, making tools for them to access and map data. So as they go out to the different nesting sites, do their observations, now we have an app for them where they can zoom in like we did earlier in the video, zoom into that location, tag the nest in 3D, and be able to record the information that they record typically with their nest observations. And as I was mentioning, next steps, kind of looking at that onboard monitoring, kind of using some new technologies. And one of the platforms that I was mentioning that we use now is enabling onboard AI and AI recognition. So kind of with that problem in mind, why is that golden eagle population declining? Now we can start looking for solutions. And of course, now we can actually start applying it to other problems. So we've been looking at golden eagles, and of course, what do golden eagles eat? They like to eat jackrabbits. So now you can start looking at applying some of those YOLO identification or other types of learning machine models to look at surveys and identify animals from these images. Typically, these are nice kind of toolkits for biologists. Typically, a biologist doesn't know how many rabbits are out there to sustain a golden eagle population. So they do these nighttime surveys along roads, flash a spotlight, and try to guess and count how many jackrabbits are out there. By using a UAS approach, we can actually, this is flying at 2, 3 in the morning, and we can actually do transects, just like a biologist would, with our equipment, and try to get a better count farther away from the road that maybe is more representative of the actual populations that are out there. So kind of moving on to our next sort of problem that we're looking at is related to sagebrush. So being part of the sagebrush step, this is a really incredible environment, and actually a really beautiful environment. But what we've been facing with our sagebrush step is a lot of disturbance. Loss of sagebrush step to conversion to agriculture, fire disturbance, and other kinds of anthropogenic disturbances that has resulted in a kind of fragmentation and degrading of the habitat. So when we're looking at restoration, there was several fires in Idaho. In order to kind of rehabilitate those locations, they got seeds from Wyoming, they got seeds from Nevada, they got seeds from all these neighboring states, and they just broadcast the seed. So how do we know those seeds will actually survive? And will a seed, sagebrush seed from Wyoming be more compatible with an Idaho restoration effort than Nevada or some other location? What is going to help us determine long-term survivability and help us more efficiently kind of restore these environments? So that's what we were looking at kind of for this particular project, is that resilience and survivability of sagebrush. And for this project, we were working in Castle Rock State Park. Maybe you've heard of City of Rocks, it's right next door to that. And we were looking across an elevational gradient and how sagebrush species and genetic complexity varies across that elevational gradient. So with our partnership with our biologists who know all about genetics, I'm not a geneticist, but I know about remote sensing. I know about how we can use kind of what we can't see with our eyes, but we can see by using sophisticated sensors. So this is a hyperspectral sensor, 270 bands between 400 and 1,000 on the electromagnetic spectrum. Think about satellite imagery, we get about 8 bands versus 270. So this is like a spectral fingerprint for identifying different types and characteristics of our sagebrush. This would be just a quick false color composite. And across our elevational gradient in our study area, we were looking at 3 different types of sagebrush subspecies. And these 3 different types of subspecies have different, something that's called a ploidy level. And you'll see here it's referenced as 2N and 4N. And this ploidy level refers to kind of the genetic complexity of the plant, very simply. and how the plant with more genetic complexity will have a greater ability to adapt to a changing climate. So in this case, we have different plants across our elevational gradient, and they have different ploidy levels. So we were interested in mapping and identifying how this transition happens across our study site, and if we could map this genetic complexity across the environment. So with our hyperspectral data, this is what that spectral fingerprint looks like. So using that camera, we can look at an individual pixel and think of a stack of 270 pixels that we can plot into these different curves. So this is kind of a raw hyperspectral pixel data. So for each individual plant, there's those blue and red lines, blue being, I believe, 2N, and red being 4N, or tetraploid and diploid. And now we can look at, can we tease this out? Can we identify with our spectral signature the differences between those plants using this particular sensor? So with our hyperspectral sensor, we kind of get these vegetation curves from each of the plants. And to kind of do a ground control, we also used a backpack spectrometer. So on the ground, did ground surveys as well with a near-infrared spectroscopy. And our near-infrared spectroscopy gives us a kind of a longer range from an electromagnetic spectrum from 400 to 250. And then our hyperspec covers this similar range right here that we can use and compare to. So we can take these two methods of collecting this data and then start to do some analysis. So we were looking at a few different approaches. One of our approaches that we were looking at was a 1D convolutional neural network. Was one approach where we can take those diploid and tetraploid spectral curves and throw them through this 1D CNN. We also looked at spectral analysis, looking at our plants through something that's very commonly used in remote sensing, just running a PCA. And when we were collecting the data, we were looking at collecting spring and fall. And this is data over 3 years. And looking at maybe when's a good time of year to sample, and when we might see some differences starting to pull those two data sets apart. And so what we kind of learned is that we are kind of seeing best results, kind of pulling apart of those data sets with corresponding to kind of spring peak greenness of those plants. And then in fall, we have seed production. So those 2 times a year were great to kind of answer some of these questions that we're starting to ask. And what we did is kind of compare the results between the different sensors. So this is my PhD student, Kyle, who's been working on this project and running some of these models. So one of our sport vector machine SVM models was giving us pretty good accuracy results between identifying our different types of ploidy levels. So being able to use those spectral fingerprints to tease apart and find plants with those differences that actually look no different in the field to our naked eye. But with these sensors, now we can start teasing it apart. The other promising thing was with our hyperspectral, we were able to do something very similar. So even though it wasn't as big a range of spectral response, we can take this shorter response and still tease out what we wanted to in identifying those two different types of genetic complexity. And of course, we're looking at comparing these different model types and model approaches. So being able to use these machine learning, AI types approaches to help tease apart and answer this question: how best could we approach restoration, conservation of our sagebrush steppe environments across Western US? So this is, I'm going to make a plug for this. This would be a really good collaboration project for those of you that maybe have interest in genetics, the sagebrush steppe, and using remote sensing, machine learning to tease apart these different questions in looking at conserving our beautiful sagebrush areas. And of course, we can take this now and start looking at mapping out what's going on. I really like this image kind of in the middle. So down, or sort of in the north end there, along this elevational gradient, we have plants that are mostly diploid or lower genetic complexity. And then lower elevation, where it's warmer, we have that plants that have more genetic complexity. And then in this zone here is that mixing zone. So that's where it makes that prediction really interesting as far as, can we look, does that mixing zone migrate, change over time? And even in the 3 years that we were there, we noticed huge die-offs in this area. So plants that were healthy the year before were dead the next year. So that was kind of interesting to see kind of what is going on there. Why are some plants surviving? Why are some others not? So we can tease it out, look at these different plot sites. And what our big goal is to take these models and start applying them to other landscapes. So now that we have a model that we've trained on, can we take this and apply it to other environments? And be able to kind of look at different model approaches. We're also looking at different kinds of normalization of those spectral curves. How can we normalize that data to get the best results, maybe that can be comparable? And kind of the goal of looking at taking that to other places. And one of the things I really like about using this wonderful high-resolution data is that we can individually map these plants. So the resolution we have with that hyperspectral sensor, each pixel is 2.5 centimeters. Our Landsat Sentinel data, we're looking at 10 meters. So we can look at the history of a plant across the 3 years that we've been surveying out there, be able to tell its story over those 3 years. And applying some of our models, now we can take that raw image, pull out anything that's green, and then start to identify different subspecies, different ploidy levels, and then start to evaluate some of the accuracies of our models. So what we'd like to do with a project like this is take it across to other areas and see if we can identify subspecies and these genetic complexities of plants across these different environments. And then here is looking at that ploidy level. Something that we have in Idaho, and probably have that some of them here too, is common garden experiments, where we have sagebrush growing like an orchard. And so all these different plants that have been grabbed from Wyoming, Nevada, and these different locations, thrown into a common garden, and then monitoring it over time to map and record survivability. And of course, running through the analysis process, all the stuff along the way to evaluate what models are going to work the best and apply it long run or long term. What we'd like to do is translate this information for satellite imagery and look at bigger landscape issues, landscape level solutions. Of course, another environment we can apply the same kind of machine learning approach to is using that similar sensor and grabbing those spectral profiles. So again, we've been flying, of course, Idaho potatoes. It wouldn't be a talk from Idaho if there were potatoes. Looking at applying these approaches across, one of the big threats for potato plants is potato virus Y. So being able to identify and root out plants that have potato virus Y early is really important for seed potato production. So another grad student here, Mike Griffel, has been working diligently to look at identifying through these spectral curves how to tease out individual plants in the field that have PVY, and then looking at ways we can take them out and eliminate them. The interesting thing is the way they do that right now for seed potato growers, for anyone that maybe has done this before, is they walk the field and visually, even though for me I can't tell the difference, but visually trying to detect PVY in the field, pull up the plant, and that's how they manually are addressing PVY in seed potato crops. So being able to do that, address that, can help us use these tools to identify virus, to identify ploidy level, identify genetic complexity, and see how that influences some of the traits of those plants over time. Other kinds of applications that we've been using UAS for, especially with UAS LiDAR data, is addressing geohazards. So along highway and rail corridors in northern Idaho, there's been a number of derailments. In this case, it's from undercutting of the railway bed there, and that is actually grain cars that have tumbled down the slope. The light colored material is grain, and this is potentially a huge risk for some of these water courses below. Another derailment here from a landslide or rock slide knocked a diesel engine off the rails and into the river. So again, kind of using these models, these tools, we're able to look at susceptibility for landslide for different slopes across these susceptible areas. So kind of pulling out that information, using our LiDAR data at resolutions that is really incredible. So when we typically look at LiDAR data, maybe 1 to 3 meters, with a LiDAR-equipped drone, we can fly that when we want, repeat it often, process that data, and look for subtle changes. So being able to monitor those changes, in this case, one of our areas of interest, blue indicates loss, and red indicates where it's been deposited. So using these models, taking that data, processing it, and answering some of these questions, where might we find susceptibility, pardon me, or significant change. Another kind of drawing from back to the fish world, here we're looking at those spawning sites in river systems in Idaho, and developing some models, not only just for kind of thermal refugia, but looking for some of the characteristics of these different locations and why they're being chosen. One project here that was kind of fun was, this is a small desert stream there's a trout called red band trout, and we decided to fly a stream corridor once an hour for 24 hours. And looking at producing this map like above here, and those blue and red locations start to shift all through the day. And we can actually pair that with temperature logger data that we placed out there and start modeling how fish might be pushed and move through a river system during the course of a day. What we're finding is that cliff bands, vegetation, all these play a role in modeling how we can look at the bioenergetics and these thermal refugias for these different fish. For salmon, we're looking at observed red locations. Of course, generating our bathymetry and orthoimagery. Mapping depth, one of our factors we can use in our analysis. Mapping gradient. And actually with that, and one input measurement, we can actually map and create a velocity map of our river system, which is really nice. We can actually even get directions, and this is one I was really happy with. Even these little eddies was showing the eddy directions really nicely from our high resolution drone data. So now we can actually look at really cool hydrological modeling with our drone data for analysis that we can pair with temperature, and then start to answer questions about where are the successful nests, where are salmon choosing to nest, pools, riffles, what's the velocity, what's the temperature, what's the depth, what kind of habitat are those nests, or what are the salmon choosing to put the nests in a particular location. Talked a little bit, Ramesh mentioned a little bit about forestry. This is actually along one of our corridors. Here's that corridor right here where the train cars fell down the slope in the river system below. But even in something like a simple program like Envy or our GIS programs are coming up with onboard AI intelligence out of the box where we can actually do tree counts. So for this particular area, we do a class tutorial in Envy that looks at this particular LiDAR data set and is able to, with kind of black box machine learning, put a dot on each of those trees, and each dot has information about estimated kind of crown size for the tree and estimated EDH. So even tools that are on board without coding, these tools are becoming more and more available, accessible, not only through our GIS tools, but also cloud-based approaches as well. So I'm noticing that my mission planning software that I use for a lot of my different data collection, they now have specialized algorithms. You can plug and play your data, and they will use techniques that we would use for coding and be able to come up with results specific to different applications. Another kind of hydrological question we can answer with our drone-based data is looking at river contamination. So in this case, non-toxic dye is being dropped into the river for a class exercise. And you'll see some scale bars on its side. And what the students did here is they wrote some MATLAB code to look at the dispersion, the velocity, and used MATLAB to input this data, and create some answers on what river contamination might look like in this particular stream system in the Port Neuf River in Pocatello. Other projects that we've been working on, partnering with project partners like World Wildlife Fund. This is a project looking at reintroducing black-footed ferret to a prairie dog colony in Montana. And so again, kind of looking at using some pretty big data sets. We can go and we can count your burrows. So in the past, we've been counting the number of burrows across these prairie dog colonies to act as a proxy for healthy populations for sustaining our little black-footed ferret. And I think the first time I did this project, about 6 years ago, or more now, I thought, oh, how many burrows could there be? And then looked at the imagery and was, oh my gosh, there's like 10,000 burrows in one little, prairie dog colony. And so we very quickly developed some tools to, at that time, use a segmentation process, use some of these rural-based, OBIA, object-based image analysis to pull out those burrows and provide a count. We just flew this quite recently again to kind of look at the change in the colony size. And so here we can kind of take our orthomosaic and our DEM data. And here you can almost see like pock marks. The burrows really do pop up quite nicely. And so we proceeded to use our old algorithms to generate a burrow count. But something that we noticed this time, using a little better camera, and here's one of the burrows. If you blow it up, you can kind of see the little prairie dog shadow, right? So then we thought, well, wait, we've been using this other kind of machine learning approaches like YOLO. Maybe we can actually do counts of the animals themselves. So that is how we're going to try to translate some of the tools that we've been using to look at this problem anew to actually count the animals themselves. And if you're not aware, prairie dog colonies have been hit hard by plague. So there's been a number of colonies that have been wiped out by disease. So being able to kind of do a count of the actual animals instead of just the burrows is also an important component of seeing how healthy that prairie dog population is. The other nice thing about drones for this colony is we can distribute drugs for the prairie dogs. So drop tasty little morsels across the colony that the prairie dogs will eat and help them combat disease. So I hope this really kind of gives you a sense of some different broad range applications, how we've used machine learning kind of to solve these complex problems. Sparked some interest in remote sensing, learning more about these tools, and how we can kind of bring it all together and work across disciplines to solve these complex challenges. And from there, I'll open it up for questions, and thank you for your attention.
So with collecting the data on the invasive species and stuff like that, have you been able to produce a file to where you can share that so you can do prescription treatments with drone applications?
Yeah, so that's actually really, the potato virus Y is a really good example. So even though visually we can't see those locations, or visually see it by using that spectral fingerprint, running it through our algorithms, we can actually get a dot for where the infected plants are. And our dream is, and I think there was some, I noticed on your website you had a spraying drone.
Yeah.
So I was really excited to see that. I was like, oh, that's what we need to actually send that drone out to our GPS location. So instead of having to have a human go out and pull a plant, you could actually send a secondary drone to go out and treat that plant right in the spot, apply like a killing agent, and then, boy, you could treat a crop pretty efficiently once that section's done.
Yeah, because right now we're basically getting requests for bids for treating BLM ground, and it's just to go out there and spray everything with pre-emergent for the invasives, and it's, well, like the last one was 2,500 acres. The cost of the chemical is $110,000 by itself without paying somebody to spray it. That's just buying the chemical it by itself. So if we could do spot treatments, that would be a lot more cost effective for everybody and a lot less chemicals in our watersheds.
Yeah, that's such a great example of how not only is being able to use these algorithms to identify invasive plants, diseased plants, sending out the treatment for those in a spot treatment. It's better for the environment and it's cost effective.
And we're doing prescription mapping on fields already on agricultural. It just takes a long time to get that data set to develop the map. I mean, you fly one day, it takes 3 to 5 days before you get the data set to go out and do the treatment appropriately.
Yeah, with some of that prescription for the agriculture, having access to high performance computing slams that data out pretty fast, which is really nice. The other good example with the potato virus Y is the way they treat the spread of the PVY. Like you were saying, it's a blanket treatment, and aphids spread PVY, so they just blast pesticide across the whole crop, which is expensive and gets in the groundwater and other contamination issues.
And I say the problem is they want to use ground rigs, and the drones use 25% less chemical, but they don't want to get to the new technology because farmers are farmers.
That is, you know what, that is something I've noticed with our cooperating farmers. They're very frugal, and they're very, they want to be convinced on the return of investment. So if they're going to put time and effort into something, they really want to see that it's going to be something that's proven and really be cost efficient.
I can get with you and get you data, but we're using about 25% less chemical using a drone than a ground rig.
That's impressive.
So cost and effectiveness.
Jeff?
Thanks so much for your talk, Ruth. That was really great. Question about sort of training students, and it's such an interdisciplinary field, and there's so many different places that the technology can be applied, and students have different understanding of things like physics and the engineering. What are some of the successful strategies that you've found for developing literacy for students in this field, both undergrads and grads?
Yeah, so for both undergrads and grads, drones are exciting. So being able to kind of participate and get involved with actually the data collection, kind of understanding the problem. But what's really been helpful is having a foundational knowledge. So because we really approach these problems from the remote sensing side of things, our students are coming in to take a 4th-year drone as an undergrad class or a graduate level class. They've had introduction to remote sensing, so they understand about the electromagnetic spectrum. They understand some simple processes about combining bands and doing some simple analysis. So they've got that fundamental knowledge that provides that basis so that when they come into the drone program, they've got the skill sets and they're ready to attack it. So being able to have that foundational knowledge from our GIS and remote sensing classes really provides and prepares them well for that aspect of it. But I do have students that also want to attack it from more of the sensor integration or looking at more from the mechanical side. And that's where we have a College of Technology partner where they can do some of the component and sensor integration and working more on the kind of nuts and bolts, if you might say, of the application for those types of equipment and sensor integration. Students from physics automatically come in with great knowledge of electromagnetic spectrum, so they also end up with a fundamental knowledge that they can bring to our classes as well. And we're finding the same with civil engineering students. Again, they have the fundamental classes, they can come in and dive right into that data analysis. And you know, some students from different disciplines also come in with, you know, different levels of computer science knowledge. So sometimes our remote sensing and GIS students are used to using our kind of canned programs, and it's a little more of a step for them to go into Python and other toolkits. So, but bringing across these different disciplines, and that's often the composition of our class from these different areas, and having them work together has really been a good experience for them as well.
I was curious, particularly as you think of kind of scaling up some of these approaches to bigger areas, what do you see as the big bottlenecks, I guess from just a pure time point of view? Like if there's sort of like collecting the raw imagery, data, photogrammetry, stitching pilots, and then maybe some machine learning kind of final processing, where, what's the big time cost currently as you're trying to scale this?
Yeah, you know, a good example would be that sagebrush scaling up. So when we're flying that hyperspectral sensor, we're flying maybe 75 meter by 75 meter plots and really mining these plots that we fly. But you know, each of those data sets is 50 gigs, as I was mentioning. What we're hoping to do is take that knowledge, what we find from the analysis of the bands, okay, what are the key essential bands that are contributing to identification of genetics or some component that we're looking for. Now we can take that up to a 10-band sensor on my drone, the fixed-wing drone, fly a larger area. From that 10-band sensor, little bigger pixel size, I can take what bands make the most kind of combinations to, again, predict that for ploidy level or species, to give another kind of idea of what we can model. From that sensor, now we're hoping to take it to a satellite sensor and look at this kind of super pixel resolution and trying to address going to larger areas by kind of using that approach from a very centimeter based and then kind of crawling up and looking at different scales and resolutions to look at larger landscapes. So that's kind of our next approach that we're looking at.
Any other questions? Or, oh, ask as many.
And I'll ask this and I'll warn our CSU guests that I might ask you to respond to, but I've been thinking a lot about partnerships over the last year, and I know partnerships with government and partnerships with the private sector. And you know, for both experiences at Idaho State and at CSU, I'd be interested to hear sort of what some of the strategies are when we're working in this area of digital innovation and how we connect to, you know, state government collaboratively and also industry partnerships that are valuable for both sides, right? And I wonder if you could comment on that.
Sure, and you know, at the beginning of the talk when Ramesh was introducing me, he mentioned this America View network. So America View consists of about almost 40 states now, and Idaho View's one. Ramesh is in charge of the Wyoming View, and what the whole goal and purpose of these organizations is to bring together BLM, bring together all the kind of federal agencies, USGS, other agencies and private partners, along with academia. And the nice thing is that through this network, we're actually able to plug into, oh, I know that person who's doing this in Nevada. I'll plug you into who's doing it in Idaho through that connection. So by having this sort of national connection, we are able to kind of plug into a network and find out who's doing what, where, by bringing together our remote sensing and GIS experts from across the nation. Has really been helpful to kind of leverage and build out existing partnerships that our neighboring state maybe has already initiated, and kind of putting those feelers in that network out has really been a really great aspect of this particular organization.
Sure. At CSU, we've built the Data Science Research Institute to try to bring people at CSU together to have partnerships in the same way. I can imagine there might be an opportunity for some kind of meta institute that would allow folks who have complementary interests and abilities to get together. So, for example, you just mentioned feature selection. And we've done a lot of work actually in the last 10 years doing feature selection on hyperspectral imagery. So there might be an opportunity here to already discuss that. And as a mathematician and knowing that sometimes there's some pushback against mathematics, it turns out that there are ways to look at hyperspectral images using subspaces that take PCA plots where points are overlapping and actually pull them apart, and you can get separable data, views of data that actually look like they're, if you look at them directly, look like they're all mixed up. So I'd be happy to chat with you about that if you're interested. But I think your question is great. How can we build on this workshop? And we're hoping to have a workshop next fall at the same time in Colorado State, and hopefully bring in some of the same folks. And oh, sorry, three.
Any other questions for Donna? Right. If not, so don't. Yeah. So I was just amazed with the range of applications she presented. As you were talking, Donna, I was just waiting what is going to come next. So if you had shown one application or anything to do with anthropology, digging for sites and all that, and if you have chased any suspects with the drone, you would have covered all the topics that we had talked yesterday. All the speakers, I was just amazed to see how many areas you touched in terms of applications and what you have done, both not just flying the drone, but also processing it. It was just an amazing talk. And as always, now you know why we don't miss any annual meetings, that America View annual meetings, because we get to go and listen to people like Donna every year. They come and tell all the cool things they did. Now recently we started bringing students, and they are also showcasing, hey, here are the things that we learned. So it's an amazing journey. So next year, they're still finding, she's in the board. She might be able to give some insights, like where America View is going to meet. But I have a gut feeling that has something to do with cheese. That's my insider information I heard from someone. So I will announce when the meeting dates are published. So if anybody is interested, please come to our annual meetings. It's a great one. And so the other person representing the family is Maddie. She's part of the Vermont View. And so we used to have Jarlath, who used to come to our meetings, and now Maddie is representing. And of course, America View is funded by the USGS, so our first keynote speaker is also closely connected to the America View family. Sorry, I took a lot of time to pitch about America View, but thank you so much, Donna. We want to... Yeah, thank you. And I understand there's still a lot more of those, what do you call them, muffins and others. So please take them when you are going to watch those demos. Yeah, there are no restrictions. You can eat and watch. Take any beverage that you prefer. And thanks once again for coming. And Jeff, yeah.
People need directions to where they're going next.
Oh, yeah. So, yeah, there is a bus, I think, that's going to take people to the recreation fields. So I think yeah, the workshops are the easy ones.
Workshop in the agriculture building, but there's also the drone pilot, drone demo, which is on the south field. If you use the QR code, on that QR code, there's actually you can click on map, and it'll pinpoint directly to where.
And for workshops, you were required to sign up before.
Yes, no,
You already know that you are going to a workshop night.
So I was going to ask that, thank you guys, who signed up for workshops, So we have 2 back-to-back workshops.
I could walk with them.
Perfect, yeah. So please follow her, and please take all the snacks you can, and then you can take. And I think they start at 9:30. So those who signed up for workshops, so I think we'll have
You only have 3 minutes.
No.
Pick up your muffins and find me.
No, 9:30, yeah, okay, please
I
go.
walk 5 minutes.
Yeah. And those who signed up for the demos, I think, well, did they say in front of the union the bus is going to come? Yes. Where about the campus? So the bus will come in front of the union. You can take the bus to the recreational fields. That's where the demos will happen. So that's the campus shuttle bus that's